Hello everyone, welcome to SS Talks Chemistry. I hope you all are doing great. So guys, we have started with the previous year questions of the CSIR NET, and in that the unit we have started was the chemical thermodynamics. Right. So it's part 1 we have already discussed, where till the year that was CSIR NET exam conducted in the December month of the year 2015, till that questions we have done. Now from the 2016 paper till the last, that is 2025 questions, we are gonna discuss in this particular part. Okay. Before this, if you have not watched the previous part, you can check that playlist is there on the channel. Okay. Or I provide the link in the description. Even from that you can get the access to that. So let us begin with this part now. So question it says del H by the del P at the constant temperature. So this temperature term it is not present over here. It's present outside. It has the dimensions of, right. Now del H by the del P that you have, this you find it using the second thermodynamic equation of the state, right. So according to the second thermodynamic thermodynamic equation of the state, equation of the state, we derive this del H by the del P at constant temperature. We want to see the complete derivation, how you can find the second thermodynamic. That too we can see it using the Maxwell square. We do this. Good people have studied under very amazing teachers, right? So dH now it is dependent upon the entropy and the pressure. So it is ds and the dp. Now opposite of the entropy is the temperature, arrow is going towards it, so positive it will be there. Now opposite of the pressure is the volume, arrow is going away towards it, so this it will be there. Now at constant pressure we are looking upon, at constant pressure it means dp value it's gonna be 0, right. So we need is del h by the del p at the constant temperature we have to do it. So differentiate this with respect to your pressure terms. So it will come out to be as temperature into the del S by the del P at the constant of the temperature plus of the volume into the del P by the del P at constant of the temperature. So here it is not the constant pressure, it was at constant temperature. That term is not included, so this we can omit it. So del P by the del P, this will be equal to the unity only. Now temperature into the del S by the del P at constant temperature. This you can replace it. Now this is del S by the del P. Like this we have written. So this could be replaced with the del V by the del P. Right. So it will be equal to temperature into the del V by the del T at the constant of the del V by the del T at constant of the entropy. Now arrow is going away from the entropy term, so a negative sign it will be placed plus of the volume. This is your second thermodynamic equation of the state, according to which del H by the del P at constant temperature it is minus of the T into the del V by the del T at the del V by the del T at the constant of the pressure plus of the volume. This is my second thermodynamic equation of state. Complete derivation part of it. If you at some point forget it, that then this way you can do it. Okay. So now I have to find is the dimensions of this. So here you can see volume term it is present, right. So now same terms it can be added or it can be subtracted. So from the volume, this will be also having the units of the volume only. So from the volume, a particular volume is being subtracted. Overall the value we are gonna get is of the volume only. That means del H by the del P at the constant temperature, it has the dimensions of the volume, right. So based upon this, our answer it's gonna be the option B in this case. I hope it's clear. Next, this question now for the ideal gas at 300 kelvins. So temperature we have kept to be at 300 Kelvin, which means temperature we are keeping to be the constant only, right? So now for the ideal gases, internal energy that you have, it is function of the temperature only. It is function of the temperature only. Similarly, the enthalpy, if you talk about this, it is also the function of the temperature only. It is function of the temperature only. And the Gibbs free energy that we have, it is function of the temperature as well as the pressure. Function of temperature and the pressure terms. So here, based upon this, we can say that del U by the del V, if at constant temperature we are talking, so internal energy and the enthalpy, they are function of the temperature only, which means del U by the del T, it can be written, but del U by the del V at constant temperature, if I'm having, that is gonna be equal to the zero only, or in terms of the enthalpy, del H by the del P at the constant temperature, this too is gonna be equal to 0. The proof of this, it lies in your equation of the states again. So the first thermodynamic equation of state that we have, first thermodynamic equation of the state, it describes the relationship for the del U by the del V at the constant of the temperature. Again using our that equation, that is deriving it from the Maxwell square, we can do this question. So if you know the exact value of this value, it is equal to their internal pressure, which is equal to temperature into the del P by the del T at the constant of the volume minus of the pressure. Just like we derived the second thermodynamic equation of state, this first one we can also derive it. Okay. Just write the expression for the du, then at constant temperature differentiate it with respect to the volume, then again we will be reaching up to this particular equation. Right. So now we are talking for the ideal gases. For the ideal gases, my PV is equal to the RT if 1 mole of the gas we are taking. Okay. So here from this one pressure term, it is RT upon the volume. We need is del P by the del T. So del P by the del T at the constant of the volume, it is del by del T of the pressure term, which is RT upon the V we are having. So now R and the V, they are the constant because this differentiation we are doing at the constant of the volume. So it will come outside. So del by del T of the temperature, this is at the constant volume, this is gonna be equal to the unity only. So this is what we are getting after the differentiation. Now just substitute this in the above equation. So my pi, it will be equal to temperature into the R upon the V minus of the pressure. So you see RT upon the V, it is nothing but your pressure only. So pressure minus of pressure, it is equal to the 0. So you can see that del U by the del V at the constant of temperature for the ideal gases, it is equal to the 0. Right. So from this equation we can say del U by the del V at constant of temperature, this is equal to the 0. Option A is my right answer. So here again del H by the del T. Now this is not gonna be equal to the 0, but del H by the del P at the constant temperature, it will be 0. Right. So this is the one. Now internal energy with respect to temperature, this is again I said it is not gonna be equal to 0. Del G that you are having, it is function of the temperature and the pressure both of this. So this again it won't be equal to the 0. Okay. So option A only is the right answer in this. Moving upon to the next one. This question now. The figure describes how the Carnot engine works. So the Carnot engine that you have, the Carnot engine, it tells us about the maximum amount of the useful work done during a reversible cyclic process. Maximum useful work done during a cyclic process. Cyclic process. And this process is reversible, so we can say it is reversible cyclic process. So this process it consists of 4 of these steps. The first step you have, that is isothermal expansion. The second step we have, that is adiabatic expansion. Adiabatic expansion. The third step that you have, it is called as isothermal compression. and the fourth one it is adiabatic compression. These are the four steps. On combining both all of this, the curve that you get, which is for the pressure versus the volume curve. Suppose from the point A you are starting, this is the point A. This undergoes firstly the isothermal expansion, which means volume is being expanded. So it goes to the pressure. This another P point it is going. This is isothermal expansion we have done in this iso expansion. Next step from B to C if we are going. This is the adiabatic expansion. So again a change in the volume it is there to a smaller amount. So like this we can say up to this point it has gone. Next it comes back by a isothermal compression. So it goes like this, volume it has decreased. So this has reached to the point B and then it goes back to the point A through the adiabatic compression. Right. So this all are the steps. Here it is adiabatic expansion. Here it is isothermal compression. Here it is again the adiabatic compression. Right. So now in the question it has been asked a plot is given that is for the V versus the P. We have made this P versus V. They have given us V versus the P plot. Now in this plot, it starts from the adiabatic compression. It has started. So for the this adiabatic compression, it is denoted by which of the following steps, right? So here in this, close to the P, you are seeing we are having the step which is of the adiabatic compression. It is there, right? So close to the P, the curve we are having that is from B to C. This only it denotes the adiabatic compression. Okay, so it is B to C which is being shown. So the option B it is the right answer in this case. I hope it's clear. Now moving upon to our next question. The next one we are having that is this. If U is function of the volume and the temperature, then del U by the del T at constant pressure it is equal to. So in terms of the pi and alpha the answers we are having. Right. So it is said that the internal energy it is function of the temperature and the volume. Now U it is your state function that is dependent only on the initial and the final state of the system. So the exact differential for it is gonna exist. So du it is gonna be del u by the del t at the constant of the volume into the dt plus of del u by the del v at the constant of the temperature into the dv of it. Like this we can write it. So now we know that del u by the del t at the constant of the volume. This is nothing but the Cv only because we write that Cv is delta U is equal to NCV into the dt of it. Like this we write it. So del U by the del T if you are bringing you are gonna get the value of the Cv from this. Right. So this replacement we can make it del U by the del T at constant of volume is my Cv into the dt plus of del U by the del V at the constant of the temperature into the dV of it. Like this we can write this thing. Right. So now the next del U by the del V at constant of temperature. This is nothing but your pi value which is the internal pressure only, right? So it will become pi into the dV plus of the Cv into the dt of it. This is equal to the du so far we are getting it. Now du by the dt we have to do it. So du we have got it that is equal to Cv into the dt Cv into the dt plus of the pi into the dV of it. This we have got it. Now differentiate with respect to the temperature at constant of the pressure. So del U by the del T at the constant of the pressure, this is gonna be Cv. Now del T by the del T, it will be equal to the unity only plus of the pi. Now del V by the del T at the constant of the pressure we have to substitute on this. Right. So now we know that the alpha value that you have, it is equal to 1 by V into the del V by the del T at the constant of the pressure, right? So from this, del V by the del T at the constant of the pressure, it is equal to alpha into the V of it. So this substitution again we can make in this. So we are getting del U by the del T at the constant of the pressure. This is equal to CV plus of the pi V alpha. This is gonna be the complete expression. Okay. So based upon this, the answer if I see, here it is pi alpha into the V, that is with the plus, here not Cp, it is the Cv value. So option D, it is gonna be the right answer. Okay. So this question now, the parameter which always decreases during a spontaneous process but at constant entropy and at constant volume. Same type of question in the last class also we discussed. The very first question that was of the year 2011 only. There I told that the various criteria for the spontaneity. Using the Maxwell square we define it like this. So it is good people have studied under very amazing teachers. Right. So in this, the energy terms that you are having, these all are gonna be less than the zero only, which means their value it is if it is decreasing then they are spontaneous. But the parameters which are constant, they differ in all of them. Now, if I talk in terms of the Gibbs free energy, it will be at constant temperature and at constant pressure. So we write like this, delta G at constant temperature and pressure it is less than 0. Similarly for the Helmholtz free energy, we write in terms of constant volume and the temperature. So delta A at constant volume and temperature it is less than 0. Internal energy, it will be constant at the entropy and the volume, it will be less than 0. Now the delta S in terms of that, it will be at constant entropy and the pressure, it will be less than 0. Right. So now we have been given the constant entropy and the volume. Based upon this, we can say that it is the internal energy, it should be less than 0. Right. So from the options if I see, it is gonna be the option A in this case. Okay. Next, this question now. The equation of state for 1 mole of the ideal gas it is given, where B and the R they are the constants, the value of the delta H by the del P at the constant of the temperature. Again using the second thermodynamic equation of the state, thermodynamic equation of the state we can solve this. Right now we know that del H by the del P at the constant of the temperature, this is minus of the P into the del V by the del T at the constant of the pressure plus of the volume term. This is what we have as per my second thermodynamic equation of state. Now the value we have been given P E minus of P into the P minus of B, this is equal to the 30. I have to find the value of the del V by the del T at the constant of the pressure. So open this, it will be PV minus of the PB, that is equal to the RT. So now its differentiation, I am continuing on the next slide. It is PV minus of the PB, that is equal to RT. Differentiate this with respect to the temperature, because del V by the del T we have to find it at the constant pressure. At constant pressure. Differentiate this. So PV, first function as it is into the del V by the del T at the constant of the pressure plus of T. Second function as it is, that is the volume as it is, del P by the del T at the constant of the pressure. So now pressure here it is constant, so this term it will be 0 in this case, right? Now similarly, now P and B, these both are the constants only. So here if I do the differentiation of this PB with respect to temperature, this again it's gonna be the 0 only. This is equal to R into the del T by the del of Pt at the constant of the pressure. So it implies pressure into the del V by the del P at the constant of the pressure, it is equal to the R, because this term is unity only, right? So from here, del V by the del P at the constant of the pressure, it is R by the P. So this value we have to substitute in our this expression, right? So this we can do the labeling of this. This is equation number 1. This we have derived. The equation number 2. Substitute 2 in the 1. Substitute 2 in the 1. We are getting del H by the del P at the constant of the temperature. It will be minus of the T into the R upon the P plus of the volume, right? So RT by the P value, this we have to note it. So P into the V minus of V was RT only, right? So from this RT by the P, this is gonna be equal to V minus of the P, right? So this substitution now we can make it over here. So it will be minus of V minus of V plus of the volume. So it becomes minus of the volume plus of the V plus of the V. So this negative and positive volume gets cancelled. So del H by the del P at constant temperature, del H by the del P at the constant temperature is equal to the V. So this is gonna be my answer. So that implies option B is the right answer in this case. I hope it's clear. Now let us move upon to the next question. That is this one. So the question it says the partial derivative which is of the del T by the del V at constant of the pressure. So now if I look upon to the Maxwell square for this, it is good people have studied under very amazing teacher. This is the mnemonic that we make use. So here del T by the del V. So here you see del T by the del V. So now opposite of this temperature is this entropy term. So using this we can find this particular value. But we need is del T by the del V at the constant of the pressure. This using this particular thing we are not able to do it. So for this we make use of a theorem which is called as the reciprocity theorem. Reciprocity theorem we make use in this. According to this theorem, you have if the del x by the del y, if you are having at a constant of the z value, if it is there, this is equal to 1 upon the del x upon the del of the y at the constant of the z value. This both things they are equal as per this theorem, or we can say we can write it in this particular form, that is del y upon the del of the x at the constant of the z but with the inverse side, right? So this thing you can make use, that thing only we are gonna use for the solving this, which is del t by the del v, del T by the del V at the constant of pressure. This can be written as 1 upon the del T upon the del V at the constant of the pressure, right? Or we can write it del V by the del T at the constant of pressure but with the inverse sign, right? Now using our Maxwell square, which is this, good people have studied under very amazing teachers. From this del V by the del T value at constant of pressure, del V by the del T at constant of pressure. The opposite of the volume is the pressure term. So a negative sign it will be placed because arrow is going away from it. This is equal to del S upon the del P at the constant of the temperature. This thing it will be there. So this substitution you can make it. This is gonna be del S upon the del P at a constant temperature. Now a negative sign it will be there. The inverse is remaining as it is, right? Or we can say this is equal to minus of 1 upon the del P by the del S at the constant of the temperature, like this we can say it, or it is equal to minus of the del P by the del S at the constant of the temperature, right? So that means del T by the del P at the constant of the pressure. This is minus of the del P upon the del S at the constant of the temperature. This is gonna be the relationship. Okay. Based upon this, the correct answer it is del P by the del S at the constant of temperature. So minus of the del S by the del P at constant temperature. Option A only is the right answer. Got it? Next. This begins from the year 2017 questions. The correct statement for any cyclic thermodynamic process. Cyclic processes means if from the particular initial point you are starting, following a certain route, you are coming back to the final position only, which means cyclic rule you have followed. The initial and the final position are the same. Suppose this is the point A. From this you are starting, you are going like this, a particular route you are following in this, like this. So here again you are coming back to the final position only. This is again your initial and the final position, which means the cyclic process it is there. Okay. For the cyclic processes, for the cyclic processes, if we have a state functions that depends only on the initial and the final state of the system, their delta, like the delta U, you have delta G, delta H, these all terms like this, it is equal to the zero only. Whereas for the path functions, if we talk about path functions, the functions which depends on the nature of the path which the system has followed. Examples, we have the work, heat and the heat capacity and the heat capacity. All these three are your path functions. Rest all the thermodynamic functions are your state functions only. That means for these types of the works, that is either the delta W, it is not equal to zero because it is dependent upon the nature of the path. Or we can say del dW, it is not equal to the zero. Similarly, the dq, if you write it, this is not equal to the zero. Or the d of the C value, that is at constant volume or at the constant pressure, this is not equal to the zero. So this scenario it is there for the path functions. So here we have to just choose the path state function only so that this condition it could be satisfied. So del Q it is written to be the zero, that is the incorrect. dW is zero, again not for the cyclic process because these are your path functions and not the state functions. Du is equal to zero, this option will be the right answer. Okay, this is how you look for the cyclic processes. Okay, now the next we are having, that is this question. So this question, it says the fugacity of a real gas, it is less than the pressure of the ideal gas at the same temperature only when the only when which of the following condition is satisfied, where TB it is given to be the boils temperature of the real gases. Okay. So fugacity, it is the pressure of the real gases. It is pressure of the real gases. Whereas P, it is the pressure that is of the ideal gases. Pressure of the ideal gases. The ratio of these two, that is the phi value you define it, which is called as F upon the P. This is called as the fugacity coefficient. Fugacity coefficient. This is the whole concept. So now here it is saying that fugacity of the real gas, it is less than that of the pressure. That means F value it is less than that of the pressure, or we can say F upon the P value it is less than the 1, or we can say that phi value that you are having it is less than the 1. So that means pressure which is of the real gas, it is gonna be lesser as compared to the pressure of the ideal gas, right? Pressure is gonna be less because in the real gases there is some attraction or the repulsive forces are there, depending upon which of this it is gonna be dominating, the resultant fugacity you are gonna get in this. Now since fugacity it is less, which means the pressure which the real gases by colliding with the walls of the container that they are exerting, it is gonna be less, which means the attraction between them it is more. Attraction is dominating as compared to the repulsion. That is why they are not colliding to the walls to a lesser extent. So lesser pressure is being produced by them, right? So attraction is dominating in this case. So that is possible, which is at which of the scenarios the attraction it is gonna be dominating, that is at the low pressure, because they are producing low pressure. So at the low pressure attraction it is dominating. Now the about the temperature. So Boyle's temperature that you have, it is equal to A upon the RB, where A and B are the van der Waals constant and R is by gas constant. A tells us about the amount of the attraction present between the real gases. So now we have said that attraction it is dominating. So if A value it is increasing, that means the Boyle's temperature it is gonna be increasing in this case, right? So that means TB value that you are having, it is gonna be more as compared to that particular temperature. So TB it will be more than that of the temperature. So the condition we are having, that is at the low pressure, but TB it is greater as compared to BT. So option B it becomes the right answer in this. Okay. Next, this question now. The minimum work which is required by an engine to transfer 5 joules of the heat from reservoir which is at 100 Kelvin to the one which is at 300 Kelvin. So temperature of the hot body. Now from a colder body, that is the one which is at the low temperature, heat is transferred to a body which is at the higher temperature. Right. So that means this question is from the heat pump. It is from our heat pump concepts. So the temperature of the hot body it is 300 Kelvin and the temperature of the cold body that we have it is 100 Kelvin. Right. Now the amount of the heat which is being transferred. So that means minus of the QC value it is given to us which is gonna be equal to the 5 joules of this. Right. So here now for the heat pump the efficiency we have which is equal to minus of the QC upon the W of it, and in terms of temperature this is equal to TC upon the TH minus of the TC of it. Like this it is there. So now the work we have to find it. Rest all conditions are given to us. So just substitute the values and find your answer. Minus of the QC value it is 5 of the joules upon the W. This is gonna be 100 upon the 300 minus of the 100. That is gonna be 100 upon the 200, which means efficiency is half only. Right. So from this we can correlate that 5 upon the W it is 1 by D2. So work done is of the 10 joules. So this is gonna be the work done. That makes the option B to be the right answer. Okay. Next, this question now. Enthalpy it is equal to. So now we know that Gibbs free energy that we have, change in the Gibbs free energy, it is delta H minus of the T delta S of it, or we can say the Gibbs energy is H minus of the Ts of it. So from this enthalpy it is G plus of the Ts of it, right? So from the options if I see, none of the option it is there in which is involving the Gibbs free energy. In terms of the chemical potential it has been written, that is mu I, right? So we define it that the chemical potential of the ith component, it is the one which is change in the Gibbs free energy that you are having by adding the Ni components in this. So from this the Gibbs free energy we can say it is summation of mu I into the Ni of this. Like this the substitution it can be made into this, because number of the ith components that you are adding, based upon that what change in the Gibbs free energy, that is what the chemical potential it denotes. If n number of the I components we are adding, so all of this it will be contributing to the Gibbs free energy factor, right? So H can be written as summation of the mu I into the Ni plus of the Ts of it. So this is gonna be the enthalpy, right? So based upon this, the options if I see, so first is extra PV factor has been included. That makes it to be incorrect. Ts plus of summation of the mu I into the Ni, option B becomes the right answer in this. Okay, next, this question now. This is from the December exam of the year 2017. The stretching of a rubber band, it is dg is equal to vdt minus of the sdt plus of the fdl. Which of the following relationships is the true one? Okay. So there is nothing new in this. Just like in case of the open systems we talk about, open system, we used to write it that the gives free energy, it is will be dependent upon the function of the temperature. It will be function of the temperature, pressure, and the ith components of the if we are adding in this. That is, matter is also included in the open systems. So dg we used to write it, that is it is vdp minus of the s dt plus of the change in the gives free energy. With this you used to write it, that is mu1 into the n1 dn1 plus of the mu2 into the dn2. Like this we used to write it, adding the ith components in this. Now instead of this mu1 into the dni, now a term which is fdl just has been added in this. This is just the difference that you are encountering in this rubber band stretching. So relationships we have to find in this. So here we have dg, it is equal to vdt minus of the sdt. So it is minus of the sdt plus of the fdl. Right. So now from the options, if you see, you need the value of this s and the f values we are needing. S and the, here is the volume, here is S and the F, S and the F. So major is the S and the F values only. So let us find it, the value of the S and the F in this. So two of the scenarios that will be there. So firstly, I am finding the value of the S. So if I take the partial differentiation of the del G by the del T at the constant pressure and the L values. So this is gonna give me the entropy value, right? Similarly, for the F value, I have to find it. So that is gonna be del G by the del of the L at the constant of the pressure and the temperature. This is gonna give me this F value, right? So now F and L I have got it. Next, we have to do the differentiation of this S and the F values with respect to the L. I have to differentiate this this S value, and F has to be differentiated with respect to the T. So let us do that differentiation now. So here we have got is del G by the del G by the del T at the constant P and L. This is equal to the minus of the S value. So differentiate this with respect to the L value now, because del S by the del L we need it, right, at the constant P and the P. This differentiation, if we do it, so we will be getting del G by the del T at the constant of the P and L. Differentiation we have done is with respect to the L. This we have done it at the constant temperature and at the pressure. So this is gonna be minus of the del S upon the del L, that is at constant P and the P values. Right. Now the other thing we have got, that was for the F value, that was del G by the del G by the del L at the constant temperature and the pressure. This was equal to the F value, right? So now we need is F upon the T value. So differentiate this with respect to the temperature at constant P and the L values. So we are getting that del by the del T of the del G by the del L at constant temperature and pressure. This differentiation we have done at constant P and the L value. This is equal to the del F by the del T, that is at the constant P and the L values. This is gonna be there. So now we know that gives free energy, it is your state function. It is my state function, and it follows the Euler's theorem. Euler's theorem. So Euler's theorem, we know that, let me just tell you about the Euler's theorem. Euler's theorem. If you have z, which is function of the x and the y, so z is gonna be the state function, then only this Euler's theorem is being followed. That means if it is a state function, the exact differential for it is gonna be written. So we can get del dz, it is gonna be equal to del z by the del of the x at the constant of the y into the dx plus of the del z upon the del of the y at the constant of the x into the dy. This is the exact differential for it. This we can write it as m dx plus of the m dy. So now del m upon the del of dy at the constant of x, it is equal to the del n by the del of the x at the constant of the y it is there. Right. So you can see here the replacement it has been done. Now the m, it was del z by the del of the x. So this we have written as del by del of the y into the del z by the del of the x. This was at constant y. This differentiation we have made at the x values. This is equal to, now the del of the x, del by del of the x, which is del z upon the del of the y at constant of x. This differentiation has been done at constant y value. So you can see these values, this x and y, it has been interchanged, x and y, this has been interchanged in this, and these two values, which is of the x and y, it has been interchanged in this case. So both these things, they are the equal. So now this concept you are gonna make use in this particular thing. So G is my state function. So that means del by the del of the L. This differentiation of the gives free energy at constant temperature P and the L at the constant T and P. This will be equal to, now interchanging this L and the T, it can be interchanged. So del by del of the T into the del G by the del of the L, and these two it will be interchanged. This will be at constant temperature and pressure, and this whole differentiation has been done at constant P and the L value. Right. So from these two equations, that is, you can label this as the star and the double star, the left side of both of this value and this value, you can see using the Euler's theorem you are getting to be the same, right? So that means their right hand sides, they will be also equal. Okay, so the star and the double star left hand sides are the equal. So we get that the right hand side, which we got it as del s by the del, we got it as del s by the del of the L at the constant T and the P, that is equal to del F by the del P, that was at constant P and the L value. So this was the one, right? So these two things, they are the equal. So this is the relationship that we are deriving from this particular given expression. Okay, so my del S by the del of the L at constant P and T, it is minus of the F upon the del T at constant P and L. Option A is only the right answer. Okay, so this is how this was to be solved. Now, moving upon to the next one, this question. So one pole of the ideal gas, so N value it is fixed. Of an ideal gas, it is going a cyclic process, which is A, B, C, D, and the A. From the A, you are going to the B, and from the B, you are going to the. So this plot has been given. Here the curve has been missed, so you can draw this plot, which is for the volume versus the temperature plot. It has been given. So this is the point A. From the A, you are going to the B. From the B to C, you are going, and from C to D, you are going. So this is the plot which has been given. The volume and the temperature conditions has been also given. This is the volume V1, and this is the volume V2. It has been given. This is at the temperature T1, and this is at the temperature T2. Okay, so now reversible process starting from the point A through the four reversible steps as shown in the figure. This is the figure from A to B, B to C, C to D, and the D to A we are going it. So we are going in a which direction? That is my clockwise direction. So that means overall work it will be negative only, right? So now here it is saying total amount of the work done. So total work done total work done, it will be a sum of all these processes, that is work done in going from A to B plus the work done in going from B to C plus the work done in going from C to D plus the work done in going from D to E. This is gonna be the total work done. Now we know that work done is minus of the P external into the dV of it, right? Or so from this one, the processes in which the volume it is not changing. Their work done it is gonna be zero only, right? So that means in A to D, D to A process that you are going, where the volume is the V1 only. And in the process B to C, volume is the V2 only. So that means this work done it is gonna be zero and this work done is also gonna be zero because dV value is zero in both of them, right? So that means total work done, it is gonna be equal to work done for the A to B plus of the work done in going from C to D. This only it's gonna be there. Now these two processes if we see, that is from A to B. A to B you can see it is going at a particular temperature, so that means it is your isothermal, and the C to D it is also at the temperature T2, so both these processes are the isothermal. So work done in going from A to B, it is isothermal. That means the work done it is gonna be minus of the nRT. Now temperature for the work done in A to B it is T1 ln of. From A to B, the volume it is changing from V1 to V2. So V2 upon the V1 it will be there, right? Now the work done in going from the C to D, this is also your isothermal, right? Now here the temperature it is different. So the work done is minus of the nRT to ln of. Now in C to D we are going from the volume which is V2 to V1. So final volume is V1, the initial it was the V2. So this is gonna be the work done. So this substitution you can make in this. So let me just do on the next one. Total work done. Work done in going from A to B plus the work done in going from C to D minus of the nRT1 ln of the V2 upon the V1 plus of the minus of the nRT2 ln of the V1 upon the V2. This is what the work done we were having, right? So from this minus of the nr ln of the V2 upon the V1, I am trying to bringing this natural logarithmic expression in the same units. Okay. So here this plus 1 you can remove it. So here negative sign it will be coming, negative negative will become positive. So plus of the nr P2 ln of the V2 upon the V1, this it will be there. So now from this nr ln of the V2 upon the V1 it is coming out to be common. So this was at the temperature T1. So temperature difference it is T2 minus of the T1. So this is gonna be the total amount of the work done. Okay. So now based upon this options just see it. ln of the V2 by the V1 but temperature difference is T2 minus of the T1. So here ln term it is missing. So this is the incorrect. Here also ln is not there. Here we have added the temperature. Again the incorrect. Here difference it is there, but it is T2 minus of the T1 it will be there. Option B is gonna be the right answer. Okay. Next, this question now. The change in the entropy for a reversible adiabatic process. So the process we are having, it is reversible adiabatic. These processes, they are the isoentropic in the nature. Isoentropic. That means delta S, it is gonna be 0. So the option C will be the right answer. Okay. Next, this question now. So at 300 Kelvin, the thermal expansion coefficient, which means the alpha value, and the isothermal compressibility of the liquid water, that means the beta value it has been given, are this and this. What is the value of del U by the del V at the constant of the temperature? So again, the first thermodynamic equation of the state is being used. Thermodynamic equation of the state. Majority of the equations from this equations of the state only you will be acquiring it. So del U by the del V at the constant of the temperature. This is gonna be equal to pressure into the, sorry, temperature into the del P by the del P at the constant of the volume minus of the pressure. So this is the expression that we have. So now we need the value of this del P by the del T at the constant of the volume. So if you take the ratio of this alpha and the beta values, so this is nothing, it is your del P by the del T at the constant of the volume only. This thing is there. So that means the values we are having 2 into 10 to the power of 4 Kelvin inverse upon the 5 into 10 to the power of minus of 5 bar inverse. Right. So that means this value is gonna be 20 upon the 5, that is 4 units, it will be bar per Kelvin. So this is the value of this del P by the del T at constant of the volume. Just substitute this and you will be getting your answer. So del U by the del V at the constant of temperature, it is temperature into the 4 Kelvin bar inverse. Okay. Minus of the Kelvin, minus of the pressure, that is of the 1 bar. Pressure temperature is 320, minus of the 1 bar. Temperature is 320. Now Kelvin into the 4 per Kelvin into the bar minus of the bar 1 bar. So with this Kelvin, this per Kelvin term, it will get cancelled out. So it is coming out to be 1280 minus of the 1 bar. So same units are there. 1279 bar pressure it is there. So now the answer is asked in the units of the kilobars to us. So that means divided with the factor of 1000, so it is 1.279 kilobar. This is gonna be the value of this internal pressure. So del U it is 12 we have got is 1.279, 1.2 it is there. Option B it becomes the right answer in this case. I hope it's clear. Moving on to our next question, we are having that is this one. It says for a closed system in the absence of a non-PV work. So what is difference between a PV and a non-PV work? PV work we say that is the maximum amount of useful work that you are obtaining, that is during the Gibbs free and by the Gibbs free energy. So G value that you have, it is free energy change, free energy change that gives us the maximum amount of the useful work done, maximum useful work done. This is at the conditions that is at constant temperature and at the pressure. That is at constant temperature and the pressure. So this is called as your PV work. This is the PV work. Similarly, the Helmholtz free energy that we have, that is also your useful work done, and that is at PV work only, that is at constant temperature and the volume. This is at the constant temperature and the volume. Okay, so now we have to find this the non-PV work. Before this, the work that you do it, that is in terms of the internal energies that you have. As per the first law we know, as per the first law, we know that du it is equal to dq plus of the dw of it, or we can say du value, it is now dq, we can replace it as pds, dw it is minus of the pdv. So here it is the non-useful work done, because there is no mechanical work is done in this case, right? So this is the non-PV work, non-PV work. There is no mechanical work done in this case, no mechanical work done in this. Okay, so du is equal to TDS minus of the PdV. Option A it becomes the right answer. Okay, next this one now. Entropy of a perfect gas, it is dependent upon the volume in which of the cases. So entropy we know it is equal to NCV. ln of the T2 upon the T1 plus of the nr ln of the V2 upon the V1 of it. This we know it. So if we go a reverse step of it, that is the one through which we have obtained this. So we can write it ds it is equal to ncv integration of dt upon the t plus of the nr integration of dv upon the v. It will be there if I keep the temperature to be constant. If T is constant in this, so we are getting that ds value it is equal to nr into the dv upon the v of it. This it's gonna be there integrating on both the sides if you see. So integrating on both the sides we are getting that delta s it is nr ln of the v it is there, right? So we can say that delta s value it is proportional to the ln of the v1, right? So from the options, if you say the first option, it says it is independent of V, incorrect. B is saying it is proportional to V, incorrect. D it is saying it is proportional to V square, incorrect. It is proportional to the ln of the V. Option C becomes the right answer in this. Okay. So now moving upon to our next question, that is this one. So this now begins the questions from the year 2019. The question it says 1 mole of a monoatomic ideal gas. So number of moles it is 1. It is transformed from 300 Kelvin and the 2 atmosphere. So temperature T1 we are having that is 300 Kelvin. The pressure we have that is 2 atmosphere to the temperature which is T2 that is given to us as 600 Kelvin and the pressure we have been given that is at 4 atm it is going. So entropy change for this particular process it is gonna be. So again the same formula it is there delta S it is equal to NCP ln of the T2 upon the T1 plus of the NR ln of the. Now it is P1 upon the P2 of it. In terms of the volume when we were writing, so CV term it was included and it was V2 by the V1, right? But here it is in the terms of CP and the ratio is P1 by the P2. Remember these formulas, okay? So now it is the which type of the gas? N value it is 1 and the monoatomic gas it is given to us, right? So it is monoatomic. For the monoatomic gases, the CP value, it is 5 by 2 R of it, right? So this value we can substitute, N value is the 1, CP value is 5 by 2 R of it, ln of. Now T2 we have gone as 600, T1 it is 300 plus of the NR ln of the P1 by the P2, P1 is 2 and this is 4 over here. So this N value also that was the 1 only, right? So this ratio is 1 by the 2 and this is gonna be 2 over here. So it is 5 by 2 R into the ln of P2 plus of the R ln of the 1 by 2, or we can say this is 5 by 2 R ln of the 2 minus of R ln of the 2, right? So 5 by 2 minus of the 1 it will become, so 5 by 2 minus of the 1 into the R ln of the 2, that means it is 3 by 2 R ln of the 2. So this is gonna be the delta S for this. Okay. So answer it becomes 3 by 2 R ln of the 2. Option A is the right answer. Okay. Next, this question now. A non-ideal gas, it follows this particular equation. Okay. B is also a function of temperature. This is important. B is function of the temperature. The deviation of the internal energy uh, from that of an ideal gas. So what is basically this real gas and the ideal gas difference in their internal energies we have to find it out. So now the ideal gas that you have, ideal gas. So here the ideal gas internal energy that we have, it is function of the temperature only. This is function of the temperature only. Whereas for the real gases, if we talk about this internal energy, it is function of the temperature as well as the volume. So both these things are included. So for the ideal gas, the change in the internal energy, because internal energy is your state function, the exact differential you can write for this. So du, this is gonna be equal to del u by the del T at the constant of the volume into the dt of it. This way we will be writing, this is for the ideal gas. So here it will be ideal. Similarly for the d mu, now for the real gas. This is dependent upon the temperature and the volume. That is, it is gonna be del U by the del T at the constant of the volume into the dt of it, into this dt plus of the del U by the del V at the constant of the temperature into the dV of it. Like this we can write it. Right. So now this thing del U by the del T at the constant of volume into the dt. This can be replaced with this ideal function. So we can say d internal energy, that is for the real gas. This is equal to du, that is for the ideal gas, plus of the del U by the del V at the constant of the temperature into the dV of it. Right. So the difference we have to find it. Deviation means deviation in the internal energy means the difference between these two, right? So the du, that is for the real gas, minus the du, that is for the ideal gas, that is gonna be del u by the del v at the constant of the temperature into the dv of it. So this equation we can label it to be the equation number 1 only. Okay. So now del U by the del V at constant of temperature, this value, again using our first thermodynamic equation of state, we can find it. But the equation we will be making use, that is of the non-ideal gas which is given to us. Okay. So now from the first thermodynamic, thermodynamic. So you are seeing how many questions from this equations of state only it has been asked. Right. So make sure you do this very well. Equation of the state, we have that del U by the del V at the constant of the temperature. This gives the value of the internal pressure. So temperature into the del P by the del T at the constant of the volume minus of the P. So this we can say this is equation number 2. So now with the equation which has been given to us, it is P into the RT. P is equal to RT upon the Vm into the 1 plus of the V upon the Vm of it. Open this. This is only there now. Yes. So open this. It becomes RT upon the Vm plus of the VRT upon the Vm square of it. This is the equation. Now we need is the value of del P by the del T at the constant of the volume. Right. So we have got as P is equal to RT upon the Vm plus of the BRT upon the Vm square. Differentiate this with respect to the temperature because del P by the del T at the constant volume, at the constant volume. So del P by the del T at the constant of the volume, this is gonna be equal to, so now R and Vm, they both are the constant, so it will come outside. So del T upon the del of the T plus of. Now here you see R and the Vm square, these both are the constant, but the B and T, they are dependent upon the temperature because here it is given that B is function of the temperature. Right, so this thing we have to keep in mind. So it will be R upon the Vm square into the del by the del T of the B and the T we have to do. Right, so this will be given as R upon the Vm square into first function as it is, which is the differentiation of the second one at the constant of the volume. We are doing this differentiation, right? Plus of the second function as it is, which is temperature into the del B by the del T at the constant of the volume. This value will be there. So here it was plus of R upon the T. So this is my value of del P by the del P. This is at constant of the volume. Okay. So this is the value. So if you want to open it, you can do that. So it will be R upon the Vm plus of the RB upon the Vm square del T by the del P del V. This is unity only, plus of the RT upon the Vm square into the del B by the del T at the constant of the volume. So this is the expression that we are getting. So now substitute this in your second expression. So this is equation number third. You have got it. So put 3 in the 2. Put 3 in the 2. So we are getting del U by the del V at the constant of temperature. This is temperature into R upon the Vm plus of the RB upon the Vm square. RB upon the Vm square plus of the RT upon the Vm square. RT upon the Vm square into the del B by the del T at the constant of the volume, and here it was minus of the pressure. So here you see, open up this, it becomes RT upon the Vm plus of the RBT upon the Vm square plus of the RT square upon the Vm square into the del B by the del T at the constant of the volume minus of the pressure. So this whole term, if you see, RT upon the Vm plus of the RTB upon the Vm square. So this was the pressure term only, that is RT upon the Vm plus of the BRT upon the Vm square. This thing is there and these both are the same. So that means it is also your pressure only, plus of the RT square upon the Vm square into the del B by the del T at the constant of the volume minus of the pressure. So this pressure and this pressure, it will get cancelled out. So my del U by the del V at the constant of the temperature, we have got it RT square upon the Vm square into the del V by the del of the T at the constant of the volume it was there. Right? At the constant of the volume. So now this expression that we have got it, this you can label as equation number 4. So now put this back in your equation number, that is first one, because del U by the del V at constant temperature, this we want to find it, that we have done it. So put 4 in the 1. So 4 in the 1. So difference between these internal energies, that is for the real, minus of the du, that is of the ideal gas, it is equal to RT square upon the Vm square into the del B by the del T, that is at the constant of the volume, into the dV of it. Now what it is there? So it is du, that is of the real, minus of the ideal gas, right? So this is equal to RT square into the del B by the del T at the constant of the volume into the 1 upon the Vm square into the dV. So now integrate on both the sides, because exact deviation you have to find it. Here small deviation we have found it. So now this we can say, this is my equation number 5, right? So integrating on both sides, both sides, we are getting integration of the D, internal energy, that is for the real, minus of the ideal, and that is gonna be equal to integration of the R T square into the del B by the del T at the constant of the volume into the dV upon the Vm square only. So this value, which is RT square into the del B by the del T at the constant volume, it is coming outside. So dV upon the Vm square, this integration we have to do it. That is gonna be equal to minus of the, because minus of the 1 by Vm it will become, so overall we will be getting RT square upon the Vm into the del B by the del T that is at the constant of the volume. This is equal to the deviation which is for the real gas minus of the ideal gas. Okay, this is gonna be our final answer. Based upon this, the correct option, if you see, minus of the RT square upon the Vm upon into the del B by the del T at constant volume. Option B is given to be the right answer. Okay, I hope it's clear. So now the next one we are having, that is this question. It says when 2 moles of the liquid A are mixed with the 2 moles of the liquid B, that is at a temperature of 300 Kelvin, the excess of the molar gives free energy in the solution is this one. So main term is this is the molar gives free energy and the excess of it has been given, which is minus of the 1.5 kilojoules per mole. The corresponding value of the gives free energy of the mixing in the kilojoules. It is gonna be closest. So firstly, what is this excess of the molar, excess of the Gibbs free energy? Excess of the Gibbs free energy. This is equal to delta G of the mixing that you find it using the experimental methods minus the delta G of the mixing that you get it by the theoretical methods. This difference between these two is gonna give you the excess value of it. This theoretical one, we find it using the formulas. This gives excess value has been given to us. This value we have to find it out. Okay. That means delta G mixing, which is for the experimental methods, that is gonna be excess value of it plus of the delta G of the mixing, which is calculated in the theoretical methods. Right. So now we have been given as the excess molar Gibbs free energy it has been given to us. So excess value of the Gibbs free energy delta G, that is in the units of the kilojoule. This we have to find it. This value is 1.5 kilojoules per mole of it. Now in the kilojoules we need to find it. So multiply it with the total number of the moles. So see here 2 moles of the liquid A and the 2 moles of the liquid B has been given. So in total 4 moles we are having. So multiply this with the 4. So with this per mole, this mole unit it will get cancelled. Excess value is minus of the 6 kilojoules of this. Okay. So now delta G mixing theoretically that we find it. Delta G mixing that is calculated theoretical. This is equal to RT into the summation of Ni into the ln of the x. So this is gonna be in the units of kilojoules only. I'll show you that. So it is RT. Now summation means the sum of number of moles of A into the ln of the mole fraction of the A, number of the moles of liquid B into the ln of the mole fraction of the liquid B it is there. Right. So substitute these values. R is 8.314 joules per mole per Kelvin. Right. Temperature it has been given to us which is 300 Kelvins. So it is 300 Kelvins. Number of moles of liquid A it is 2 ln of mole fraction of this number of moles of this upon the total number of moles plus of the number of moles of liquid B into the ln of number of moles of liquid B upon the total number of the moles. This value it is there. So this 2 moles we are having. This also it is in the units of the mole unit it is there. So here you see per Kelvin and this per Kelvin term it is getting being cancelled out. Here we are getting 8.314 joule per mole into 2 ln of the 1 by 2 plus of the 2 ln of the 1 by 2 overall units of this bracket it is in the units of the mole only. So this per mole unit and the mole unit it will also get cancelled over here. Right. So we are having here this 300 it was also there. So 8.314 into 300 into now 4 ln of the 1 by 2 it is there, right? So this you can write it as 8.314 into the 300 into minus of the 4 ln of the 2. Solving this, we will be getting the value which is minus of 6.915. So this was in the units of joule we were getting. So if we divide it with the thousand, you will be getting in the kilojoules, which is minus of 6.95 in the units of kilojoules. Right? So this is how it was to be done. Now just substitute these values. So the excess value we have got it as minus of P6, and the Gibbs free energy theoretically we have got it minus of 6.915. So experimental value it becomes the minus of the 12.915 kilojoules of this. Right. So this is the answer, that is minus of 12.9. Option A, it becomes the right answer. Okay. So let us keep this class up to the hair only. So till the year, that is 2019, we have done the questions. I thought we would be completing it, but video is becoming the lengthier one. So let us keep this one up to here only. So from 2015 to the June 2019, we have discussed in this part. Now the remaining questions that will be still of this June paper of 2019 until the December exam, this 2025 exam, that is that. So all that questions we will be covering in the next part now. Okay. So thank you so much for watching. If you have understood the concepts, then make sure you like the video and do share it with your friends as well. And if you have not subscribed to the channel so far, make sure you subscribe to the channel also, so that you can get notification of the upcoming parts of this, and also for the new units that we will be discussing. Okay. So thank you so much for this one. I'll be meeting you in the new video now.